and welcome to Friday's edition of Cracking the Cryptic and what sounds like an absolutely fascinating puzzle today by Miky, an author I hold in high regard and I'm slightly scared of actually. I've done two or three Miky puzzles on the channel and they've always been incredibly clever in a way that makes me suspect Miky is particularly brilliant. This puzzle is called Mean World Syndrome, which I didn't know as an expression, but I've just looked it up and I sort of get it actually. I think I might have it. Mean World Syndrome is basically the syndrome that because of social media being ubiquitous, we perceive the world to be a more dangerous place than it actually is. So, you know, if you've found yourself over the last few years watching the news and just being filled with gloom and doom, I think that's a bit of mean world syndrome, if I understand it correctly. And yeah, well, it's called, but this puzzle is called Mean World Syndrome. Hopefully not because it's going to make us feel that the world is an unfair and dangerous place, but because all of these arrows are not normal Sudoku arrows. They're average arrows. I'll read the rules properly in a moment, but basically what that means is that, like, this cell here is the average of the digits on its arrow, and this is going to play with my head something rotten. I think Mark might have done an average arrow puzzle on the channel before, but I haven't done one, and I looked this up on Logic Masters Germany because I wanted to know what people have been saying about it, and hardly anyone's been able to solve it, which is slightly terrifying. And there were two comments from people who have solved it, and they were very wholesome and fulsome, I should say, in their praise. So I've no doubt this is brilliant, but I'm slightly scared of it, and I'll read the rules in a moment or two. What else do I have to tell you about? Not too much today. I'm going to start with saying that we released a bonus video this morning doing our Times masterclass series. So this is the 12th edition where we solve today's Times crossword, and today had a really nice Easter egg in it. It was all about basically the coronation of King Charles III, which happens in the UK tomorrow at 11 AM. Neither Mark or I did get an invite, but we will be watching it on television. And yeah, that crossword is really clever. It's got some lovely clues, so I definitely commend that to you. What else can I tell you? Let's do a birthday. I want to say a very happy birthday to Simon. No, it's not me. Mine's about this time next month. But Simon, your wife Mercy wrote to us and said that it was your birthday today, and I hope very much you enjoy your surprise. I think it's a trip you've got tomorrow. I don't want to say I don't know too much about it, but Mercy said that she's taking you to do something that you're going to absolutely love tomorrow. So I hope that goes well, and I hope today, of course, your day is full of chocolate cake. And the only other thing to mention is the huge activity going on our Patreon at the moment, where we've got DiMono's Jewels of Osiris, which is a novel with Sudokus that crop up every now and again in the novel, and you have to solve the Sudokus and understand what to do in order to access the later chapters of the novel. It has been going gangbusters. You've been loving that, and I understand why. If you're a patron of the channel and you've not had a chance to have a look at that, do make time. I know everybody's time is precious, and our puzzling time is particularly precious, but certainly doing DiMono's Sudoku hunt is well worth it, trust me. And that's all I've got to tell you. So now let's read the rules of Miky's puzzle. I will position my hands on my keyboard. I have my window open today, so if Maverick flies by, I'm afraid that there's going to be a bit of noise, but it's a really lovely spring day today, so I'm airing my office. These are the rules. Normal Sudoku rules apply. Circle digits must be the mean brackets average of any arrows that leave the circle. So that's what we were saying earlier. So let's actually just think about that for a moment. If this was a 5, these two digits would have to have an average of 5, which would mean they would add up to 10, is how I think that works. Seems fairly straightforward. Cells separated by a black dot contain digits with a 1:2 ratio, i.e. one digit is double the other. So if this square was 4, this square would either be 2 or 8 to make sure that one of the digits was double the other. Cells separated by a white dot must contain consecutive digits. I can't I was about to say I can't see any of those, but there is one. There is one white dot in the puzzle. So if this was a 1, this would be a 2 to make sure the digits were consecutive. Not all possible dots are given, so that means it's perfectly possible for this to contain a 1-2 pair, which could of course contain a white dot, but the fact that there isn't one there doesn't mean that these cannot be a 1-2 pair. So there is no negative constraint, as we like to say. Now, do have a go. The way to play is to click the link under the video as usual, but now I get to play. Let's get cracking. Now, if this was normal arrows, I would instantly be drawn to this arrow. In fact, this arrow would instantly be impossible, wouldn't it? And the reason this arrow looks interesting is that there are 5 arrow cells coming off the circle. Now, what does that mean? That means that, so this is the average of 5 different digits. So these digits must sum to a number that's divisible by 5. That must be right, isn't it? Let's just put a number in here and see if we can understand. So this is a 4. These 2 squares have to add up to 8, don't they? Because 8 divided by 2 is going to give us 4. These 3 squares would add up to 12, because 12 divided by 3 gives us 4. So together these add up to 20, yes. So okay, so basically what we have to do is add up the number of cells along the arrows, multiply that by the circle, and we get the sum of the arrows. And that must work for everything, doesn't it? Yes, okay, so length of the arrow is 2, so 2 multiplied by that is the sum of these digits. Right. Right, okay. So if this was 4, these would add up to 20. This was 5, this is 25. Okay, and the thing, well, I think this has got an awful lot of options. I'm embarrassed to say I don't think this is where we start the puzzle, because what I can see is that 5 different digits in a Sudoku, at a minimum they would be 1, 2, 3, 4 and 5, which adds up to 15 and would give us a 3 here. But the most these could add up to would be 35, and that would give us a 7 here. So we could go properly ham on the pencil marks and put 3, 4, 5, 6 or 7 in here. And all we know is that these 5 digits add up to 15, 20, 25, 30 or 35. I mean, what on earth do we do with that? So these digits add to 2 times this number, so they add up to 6, 8, 10, 12 or 14. No, this is not how to do this. Should we try, let's try this bottom arrow. That's a 4-cell arrow, which again ordinarily would just be shouting at me as being utterly impossible. So what we're saying here is that these 4 digits must add up to a number that's divisible by 4 in order that this can exist as an integer. Now, the minimum 4 cells can add up to would be the triangular number for 4, 1 plus 2 plus 3 plus 4, which is 10, which is not divisible by 4. So the minimum this is 12. And that would put a 3 here, and that's going to no, it's not going to break the 12 total. I thought that was going to immediately break, but it doesn't. If we put 3 in here and put 1, 2, 4, 5, that would even work with the dots. Bother. Oh, okay. 1, 2, 4, 5 add up to 12. Their average is 3. Right, okay, so the whole... that's a bit weird, but okay, that makes sense. So the whole arrow, you can look at the arrow cells and divide them by the length of the arrow, and you'll get an integer. Or you could take the circle as well and divide that by the length of the arrow and the circle, and we know that's also got to be an integer, because this is the, yeah, that's strange. So what I'm sort of saying here is if you divide those squares by 4, you get a number, let's call it x. And if you divide those squares by 5, you get that same number x, because this is just contributing the average value. So those 5 numbers are divisible by 5, and these numbers are divisible by 4. Right. Right, so these are divisible by 3, these are divisible by 4. These are divisible by 2, the whole lot is divisible by 3. Right. Okay, so I am going to claim that that cell is divisible by 3 because of the secret then. Right. Okay. So let's think about that. This is the first, I think, concrete conclusion I've had so far. And it derives from something that is secretive. And it's a secret, but I will let you in on the secret, because I tell the secret to my favourite people. Just don't share it with anyone that you don't really, really love. Now, the secret is that any complete column of a Sudoku, indeed any complete row or any complete box of a Sudoku, because of the rules of Sudoku, contains the digits 1 to 9 once each. The digits 1 to 9 add up to 45, and 45 is divisible by 3. Knowledge bomb for you there. But I've just established something about these weird arrows. A 3-cell arrow, a 2-cell arrow with a circle is divisible by 3. So this is divisible by 3, this is divisible by 3. And what do I know about a black dot? Well, it's digits in a 1 to 2 ratio. So let's think about how that works. If this was x, this would be 2, or could be expressed as 2x. So the sum of the digits on a black dot is 3x. 3x is divisible by 3, obviously. So those 8 cells are divisible by 3. The column is divisible by 3. So that cell, in order to preserve modularity, is a 3, 6, or a 9. Now, that's not going to work in the bottom row. So those 3 cells are divisible by 3 because of the black dot principle. But these squares are not, well, they're not necessarily divisible by 3. They're definitely divisible by 5. Oh! No, these are divisible by 3. Haha! In this column, we've got the same. Oh, look, it is the same as well. I just didn't notice this. Right, this column, we've got, again, we know the whole column's divisible by 3. The arrow and a 2-cell arrow and a circle is divisible by 3. That's divisible by 3. This is divisible by 3. So that is also divisible by 3. And now come back to the bottom row, because all of a sudden we have lots of stuff that's divisible by 3. Those 4 cells sum to a number that is divisible by 3. So to preserve modularity for the row, which is overall divisible by 3, this is now divisible by 3 and 5, remember? Because we said this was divisible by 5, so it's now divisible by 15. So it's either 15 or 30, because it can't add up to 45. But that's really where we got to before, isn't it? Well, it's not where we got to before. No, but if this adds up to 15, then the average value is 3, and we put 3 in here. And if this adds up to 30, the average value is 6, and we put 6 in here. I think I said the average value is 30, but the sum of the digits. Sorry, if this adds up to 30, 30 divided by 5 is 6. So that's a 369 triple. So this black dot doesn't have 3, 6 on it. So it's 1, 2, 4 or 8. Oh, of course. Right. So this is not 3. Because remember when we were thinking about how this could be a 3. If this is 3, well, I've got to put 1, 2 and 4, well, I have to put 1, 2, 4, 5 in the 4 cells that add up to 12. And then there's no way that that black dot can exist. Oh, in fact, I didn't even need bobbins. I could have proved that this wasn't 3 ages ago. Because if this is 3, we know those had added up to 12, so they would have to be 1, 2, 4, 5, because they couldn't be 1, 2, 3, 6 without repeating the 3. And that already breaks the black dot, because you can't have a black dot relationship without one of the digits 1, 2, and 3 or 4 in Sudoku. Because if you try 5 on the black dot, the other digit will be a 10 or higher, and that doesn't exist. So in fact, I've always known this isn't a 3 by that logic. But before we worked out this was divisible by 5 and 3, we didn't know the alternative was 30. So we have learnt something. We have learnt from our work. We have got a little bit of extra information, which is that this had to be divisible by 3 and 5, and that means we now know that this digit is a 6, which means these two. Now that means that one of these digits is a 3, and you know what that means? If you don't, well, the treat you're in for. Right. So these digits add up to 4 lots of this. So these add up to 24. Oh, so I can work out the value of these digits. Oh, of course I can. Oh, this is a 1-2 pair. Right, because I can just apply the secret now to the row, because I know how the row works. These digits add up to 30. Those wing digits add up to 12, which is 42. The whole row adds up to 45. So this is a 1-2 pair. That's very pretty. So now these squares are 4, 5, 7, and 8. Right, so now there's a sort of virtual white dot between these two squares, because this dot is either a 4, 5 or a 7, 8. So this is either a 4, 5 or a 7, 8. I don't really have a way of telling myself that, but it is true. There is a notional white dot between these two cells. Now, what does this mean? Oh, I just had a horrible thought. Oh no, I think it might be okay. I just had a horrible thought. I suddenly thought you can't put 1 or 9 in a circle, and I wondered whether that was going to mean that I could, I would be able to work out where the 1s and 9s went in the grid initially, just from the very start. I don't think that's true, actually. I can't see how to use... It's true that you can't put 1 or 9 in a circle, because how can you have an average value of digits on the arrow of 1 or 9? You're going to have to put a digit that's higher than 9 or lower than 1 on the arrow, and there are no Sudoku digits that meet that criteria. So I don't actually think that matters too much. I didn't notice that. Now, what can this black dot be then? It's not got 2 on it, so it's not 1, 2, and it's not 2, 4. So it's either 3, 6 or 4, 8. Right, Well, it's right, but hang on, am I wrong about that? No, I'm not wrong about that. If that was 4, 8, where do you put 4, 8 in this row? You've got to put them on the white dot here. And 4 and 8 are not consecutive numbers, so that's not 4, 8. This is 3, 6. Ah, so that's 9. Okay, so that's 9, and this is 3, and I'm expecting a party. That's 3 in the corner. That's 3 in the spotlight, losing its religion. Right, so what's that done? So we've got all the low digits here. And we've got a mixture of modularity and entropy here. Those are all the low digits from an entropy perspective. These are all the 0 mod 3 digits from a modular perspective. Okay. Yeah, okay. Now, that is interesting, actually. Is that right, what I'm about to say? I think it is. Yeah, okay. How about, is this true? So, if you've got a 3-cell arrow in one of these puzzles, or when I say 3-cell arrow, I mean the circle and the arrow are 3 cells. Then because we know that the sum of that sequence is divisible by 3, either the whole arrow is one modularity. So by which I mean, imagine this was 1, 4 and 7. Each of those digits have a remainder of 1 when divided by 3. So so this would have a remainder of 1, this has a remainder of 1, this has a remainder of 1. That's 3 remainders of 1, which gets us up to 3 again, which means the whole arrow has a 0 remainder 3. So 1, 4 and 7, if we add them up, we know that they have a 0 remainder that add up to 12. But the other way an arrow could work, a 3-cell arrow in this puzzle, is one of each modularity. And what do I mean by that? Well, I mean one of the set of digits 1, 4 and 7, which have a remainder of 1, one of the digits 2, 5 and 8, which have a remainder of 2 when divided by 3, and one of the digits 3, 6 and 9, which have a remainder of 0 when divided by 3. So if we had one of each of those along a 3-cell arrow, that would also be a possible way of doing it. But what you can't do is sort of mix and match, can you? You can't have 2 of the digits 1, 4 and 7 and one of the digits 2, 5 and 8, because the arrow won't have the correct remainder when divided by 3, i.e. it won't have a 0 remainder. So in this column, one of these is 1, 4, 7 and one of these is 2, 5, 8 because they can't have the 0 remainder digit on them. So one of these will be 2, 5, 8 and have each digit individually has a remainder of 2. So by the time you get to the end of the arrow, you've got a sort of 6 remainder, if you like, that you've built up. 6 is divided by 3, so the overall arrow works. So one of these is 1, 4, 7. And one of them is 2, 5, 8, and that's but now this might not be the place that matters. I'm wondering if it's here. Oh, I can't get my head around this. Hang on, let me think about this. This cannot be a 6-9 pair, because 6 and 9 are not available black dot digits. Well, 6 is, but 9 definitely isn't. So yeah, so this column has a different property from a modular perspective to this column, which doesn't feel right. That doesn't feel right to me, actually, all of a sudden. Oh, maybe it is. No, maybe it is, because the black dot here has taken a 3-6 pair away, which I can't put on this one. Yeah, so this does have a different modular property. What do I mean by that? What I mean is this has to be 1, because this can't be 6, 9. And I can't put 2 of 6 and 9 on any one of these arrows. Because if I did, imagine I tried to do this. So let's put a 6 and a 9. These both have 0 remainder. So in order for the arrow overall to have 0 remainder when divided by 3, that digit will have to be divisible by 3. And there are no Sudoku digits left that work. So we're going to have to separate the 6. One of the digits, 6 or 9, will be on this arrow. One of the digits will be here. And this will be one digit that's mod 1 when divided by 3, and one digit that's mod 2 when divided by 3. And that tells us virtually nothing. In fact, it tells us virtually nothing. Sorry. Because I'm suddenly realising that with the 3 here, I could have written in these options anyway, and they would automatically fulfil that criteria. I am such a doofus. Doofus, Simon. Doofus. Oh, how embarrassing. Oh, dear. Okay. So, right. Okay, well, let's change tack then. Let's change that. I'm gonna keep trying spotting things that are divisible by 3 in this perimeter. Those two are definitely divisible by 3. So that means these 3 digits have to be divisible by 3, don't they? To make sure that overall row is divisible by 3. Now that's definitely not divisible by 3 on its own. So that means that either these 3 digits, so if this was a 1, say, this would either, if this was a 1, these could have the same remainder when divided by 3 as 1 does. So if this was a 4 and a 7, that would work. Because then what we know 1, 4 and 7 are all from the same modular group. But the other way we could do this is to have so let's say this was a 1, we could have one from the 258 group and one from the 369 group. And in fact, if we did that, that would have to be the 369. Because this one couldn't be. Oh, no, this is fine. This is fine. Ah, right, so this does matter. Ah, this is pretty. There's a cleverer way of seeing this. There's a cleverer way of seeing this, but I have seen something now. Right, these 3 digits are not from the same modularity. Because if these digits are from the same modularity, what's the modularity of this 3-cell sequence? Well, the problem is that these would all have the same modularity, and there are now 4 digits with the same modularity in box 3, and there cannot be that, because there's a 369, there's 3 of those, there's 147 and there's 258. So it's not possible to find 4 digits of the same modularity, by which I mean what's the remainder when you divide those digits by 3. There aren't 4 of one type in any Sudoku box, and we know that these are all the same type because we know those are all the same type, so we can't lend a 0 remainder digit to anything on this arrow. So it's either each one of these is remainder 2 or each one of these is remainder 1, in order to make sure that the arrow's remainders are sort of preserved, if you see what I mean. So this is interesting, because now Now we need to colour each of these a different colour, because these are different modularity in order to ensure that overall we've got 0 mod 3 going on. Now, and that means this one, and that means we can label these blue, because we know that one of these has to be a 3, 6 or a 9, and it can't be that one, and it doesn't seem to be that one, so it's that one. So that's a 3, 6 or a 9, and it's not a 9. It's not a 9 because it's in a circle. We learnt that a few minutes ago. Now, all I know, I think, is that this and this, well, actually, I'm going to shade those in purple because they have the same modularity, and that's different from this modularity. Now, so this is purple modularity, and that must be true because we know those 3 digits are divisible by 3, and that is blue modularity. This is green modularity, so that must be the other modularity, which happens to be the same as that modularity. Now what do we do? So now if this was 3, that has to be a 1-5 pair. Because by maths, if this is 3, this has to multiply to 2 times 3, which is 6, and it can't be a 2-4 pair, so this would be a 1-5 pair. And that doesn't work. This is so clever. This is just bonkers, actually. I don't think I'm doing this the right way. I've got tears in my eyes. That's really weird. I think there is a different way of doing this rather than worrying about... I've done too many puzzles by full deck and missing a few cards. This is what I'm concluding here, and their puzzles are all about mod 3, you know, dividing things by 3 and what's the remainder. Well, look. Right, if this is 3, this has to be a 1-5 pair for the maths to work. But now, 1 and 5 are in different modular groups. So how could this arrow ever exist? This is either a 1-4-7 triple or a 2-5-8 triple, and whichever it is, it's killing this. So this is a 6, is what we've just learned. And now we've got the same point. This is a 3-9 pair, because 6 means these add up to 12, which means they're either 4-8, 5-7 or 3-9. Well, what they're not is 4-8 or 5-7, because again, well, let's look at 5-7 for example. 5 has a remainder of 2 when divided by 3. 7 has a remainder of 1 when divided by 3. So impossible, given that this is either all of the remainder 1s or all of the remainder 2s, and the same is true for 4-8. So this has got to be 3-9, and now this isn't 3. These are blue. So these are green then. That's forced because that's the other colour. Six is in one of those cells. If 6 was in this circle, these would add up to 12, and these would add up to 30. So these would add up to 15. These are green, because in this column we need 3 greens, and then we haven't got any at the moment. But that... Hang on. Yeah. Hang on. This is so clever. This is just... It's just really weird the way this works. It's totally unlike any other arrows puzzle I've ever done. Right, these three digits have to be divisible by 3 again. It's the same thing. So they're all of the same modularity. Or, sorry, they're either all of the... They are all of the same modularity. But they're either all of the same modularity or they're one of each modularity. But we can't put a green. There's no green modularity available for this arrow. So this is all the same modularity. But Okay, where do I put the blue modularity digits in this box? And the answer at first blush is I don't know. And I don't really know, except there must be a blue modularity digit on this arrow somewhere, because this 3-9 pair is not green modularity. I could put one of them there, but another one's going to end up on the arrow, which transforms the arrow into a totally blue modularity arrow. So now, and blue modularity is 3, 6, or 9. So this square is 6, and that means these squares are purple. And okay, so they must be a 3-9 pair. This is weird. This is absolutely weird. So now, oh, actually, hang on a minute. Is this broken? No, okay, I can't. I suddenly thought I've got to put a 6 on the arrow in this box. And I can see I can't put a 6 up here because these two have to add up to 12. But these have to add up to 18, don't they? 3 lots of 6 to keep the average at the correct level. So there's a 6 in one of these. And the other 2 digits add up to 12. And they're not 3, 9. So this sequence is one of each modularity. How am I going to... I'm going to have to record that somehow. So these are blue modularity, there's a green modularity, and there's a purple modularity somewhere there. That's one of each. Now, what does that mean? I'm not sure. I feel like I should know what that means, but I can't understand. So this is either 4, 8, 6 or 5, 7, 9. 4, 8, 6 or 5, 7, 9. Okay. I don't know what to do with that information. And I tell you something I'm feeling as I'm trying to solve this is that I have no intuition about where to look next. Whereas ordinarily in arrow puzzles, my eyes would be drawn, my eyes would be drawn here, straight away in this situation. Right, okay. Does it matter? I can work out, okay, these add up to 30, don't they? So these add up to 15. 15 in 4 cells. I mean, they have a very slightly lower than average, if you see what I mean. But it is only very slight, which isn't surprising given this is a 6. If that had been a 5, it would have been totally average. See, it's really close. This is really close to forcing 2 into green. And if we knew that 2 was green, then we would know that this was a 2, 5, 8 triple. Oh, that's true. I hadn't spotted this actually, but it's totally obvious. They're a 4, 5 pair. Oh my goodness. I didn't... Oh, good grief, Simon. What are you doing? Right. Yeah, that must be true. Although, is it true if you've got different modularities on the arrows? I think it's still true. Yeah, what I'm sort of mulling over, it feels right. It feels right. I haven't completely convinced myself. It's definitely true for this one and this one. This one has to be the middly digit from the modular set, doesn't it? because effectively on a 2-cell arrow you're going to have a higher digit than what's in the circle and a lower digit than what's in the circle. So if you think about this strip, let's imagine this was 1, 4, 7. The 4 has to go here, and the 1 and 7 provide the 8 that you need to average down to the 4. So these two digits actually are a 4-5 pair. That's what we can learn from this. Now, I think that means this is a 4 or a 5, but the top row works slightly differently, doesn't it? Because this is one from each modularity. So one of these... Yeah, how could this not be 4, 5 if it's green? So how could it be, say, low modularity from the green set, which would be a 1 or a 2? Will it? Oh, can it be a 2? Oh, it doesn't. Yeah, no, it's different. It's different because if this is a 2, this could be a 1, 3 pair, couldn't it? And because I'm borrowing, yeah, because I'm able to, yeah, because I can have available things from the same entropic set. I can't, no, okay, it doesn't work the same way. My bad. Okay, so this is not a 4. Well, it might be a 4 or a 5, but it doesn't have to be a 4 or a 5 because these two digits are definitely not from the same modular set. This is crazy. Okay, so we've got 4, 5 here, 4, 5 here. So there's a virtual 4, 5 pair in these 4 cells. Oh, hang on, this is struggling here. But these cells down this column are different. They have different... Ah. That digit is not 4, 5 or 6, is it? So this, well, that's okay because this column has funny entropy possibilities. Yeah, because this column is like this row in the sense that every 3-cell arrow has one of each modularity on it. Yeah, okay, but that cell is quite restricted actually, I think. Because it can't be, by Sudoku, it can't be 3, 4, 5 or 6 because there is a 4 or a 5 along this sequence because it's either 4, 8 or 5, 7. That will join its friend here. So there's a 4, 5, 6 in those 4 cells. So there's not 4, 5, 6 here. There's not 3 here. We know there's not 1 or 9 in a circle. Now if we put 2 there, that doesn't work because 2 requires these 2 cells to add up to 4, which would require a 1, 3 pair. So that doesn't work. So this isn't 1, 2, 3, 4, 5, 6. So it's 7 or 8. It's not 9, so it's 7 or 8. So these two either add up to 14 or 16. Now if it's 16, this would be a 7, 9 pair. This would be an 8. This would have to have a 2 on it. Ah, so there's right, now there's a virtual 7, 8 pair in this row. Because this arrow, well, this arrow consists of 6 and 2 cells that add up to 12. So there's got to be a 7 or an 8 here, because there can't be a 3 or a 9. So we've got 4, 5, 6. So right, so between these cells, we have used up in the row 4, 5, 6, 7 and 8. Oh my goodness, I've done it. Right. What's that cell? That is one of the greatest naked singles in Cracking the Cryptic's history. For me, anyway. That's a 1, isn't it? Look, because this row consists of... those digits are a 4, 5, 6, 7, 8 quintuple. So these digits are from 1, 2, 3 and 9. That cell sees 2, 3 and 9. So that leaves 1. And if that's 1, purple is 1. So the purple set is the set of digits that have a remainder of 1 when divided by 3, i.e. it's 1, 4 and 7, which means this is 4, this is 5, this is a 1, 7 pair, this is a 2, 8 pair, this is a something, brain won't be that quick, 4 and something, 4 and 7 maybe? Yes, okay. Why didn't I do that by modularity rather than doing it by Sudoku? It turns out I'm better at modularity than I am at Sudoku. Famous last words. Okay, this is 2, 5 and 8. Can that really be 2? No, it can't be. Again, it would be better to use Sudoku to think about that. I was thinking about whether this could be a 1, 3 pair. But this is 5 or 8, so 2 is here, 2 is here, 2 is now green. We can greenify it. So what's going on in this column? We need one green and 1 purple here. So I thought we could get that digit, but we don't know what that is. That's got all sorts of possibilities that are both in the green and the purple set. Okay, so these are not 1s. There's definitely a 2 over here, look, because we've got a 2, 3, 9 triple left in this row. Where's 4 in this row? Where's 4 in this row? It's got to be on this arrow. So this has got 4, 8 and 6 on it. It's all even numbers. So this is 4, 6, 8. That's not 6. This is 7 now at the start of the column. 7 is a purple digit. We know that this arrow's got to have one of each, doesn't it? Because we didn't have singular entropy or singular modularity coming down this column. Oh, we can do this black dot. Green is from 2, 5, 8. So okay, the top digit is 2 or 8. This digit is 1 or 4. And this is 7, so these two squares add up to 14, so they're either 5, 9 or 6, 8. So if that's 8, 4, this is 5, 9. That doesn't work. If this is 8, 4, and that forces this to be 5, 9, and that leaves 1, 2, 6 on this arrow to be placed in the column by Sudoku. But there is no way. There is no way to make that work. They are of different modularity, but there is no way to make the averaging work. I can't put anything in here that's going to make this work, this arrow. That doesn't work at all. So this is not 8, 4. So this is not. So this is a 2. Oh, that still doesn't give us this digit, does it? Whatever I put in here, it doesn't actually affect this arrow now. Right, hang on. So this is 2. Sorry. I don't know actually what that means. Okay, so I already have achieved the modular effect that I was looking for. Bobbins. Okay, so let's instead of that think about this square. Let's think about this square. So this is 5 or 8, which means these two digits either add up to 10 or 16. So if this is 8, this has to be 7, 9. So this would be 7, 8, 9, and this would be 1. And this would be 3, 4, 5, adding up to 12, and we could put the 4 there and a 3, 5 pair, and that would work from an averaging perspective if this was 8. But if this is 5, these have to add up to 10, and they can't be 2, 8 or 4, 6. So they're either going to be 1, 9 or 3, 7. So those digits are always odd, actually, because if that's 8, that's 7, 9. And if it's 5, they're 1, 9 or 3, 7. One, 9 or 3, 7. I don't know how to do that. Do I literally have to go through all of the options? If this was 5, 1, 9, this would be 7. I can't remember what that means I've got over here. Or is it this column? I thought about this a moment ago, though. I don't think I can do much with this arrow. I've probably missed some Sudoku, actually. Let me think about that. Can I get those digits? Yes, I can actually. I can do that very easily. These add up to 12, and they're not 4, 8 or 5, 7, so they're 3, 9. Okay, so this row now might be where we have to look. 1, 2, 5, 6, 8. So this square is 1, 2 or 5, I think. It sees 6, it sees 8. 2, 5. Oh, I thought I was going to get 2 in the row, but 2's still got 2 possibilities. No, this is getting icky now. I don't think I'm finding the natural next place to look, because everything so far has been baffling but brilliant when we found it. It's been really incredible. Does it matter that these two are both odd? I've got 3 odd digits in the row, for sure, in those 3 squares. So I need 2 more. That could be one of them. And then I'd have 1 odd digit over here. Ah, okay. No, maybe it's the even digits then in this row. 4 and 8 I've not put into this row yet. So, let's think about how we can populate one of these 3 cell arrows. Now we can absolutely put an even digit in a circle, but if we put an even digit along the arrow, we have to accompany it with another even digit, because if we put an even and an odd digit on the arrow, this is not going to be an integer, because this is not going to be divisible by 2. So, and this is it. That's it. It's simple. It's simple. So in this row we have 2 choices. We could put both of the even digits that we've got remaining on an arrow, but that's putting 4 and 8 on an arrow. 4 and 8 add to 12. The average of them is 6, and that would put 6 in a circle, which we can't do. So we've got to put the remaining even digits not on arrows at all, which means they go in those 2 squares, which means this square is an 8, this square is a 4. This must be a 7, 9 pair now. That's the only way to achieve an average of 8. Which means this square is a 1, this square is a 7. These squares are a 3, 5 pair by Sudoku. Come on. This circle, maybe? 4, oh no, there we go. 4, 8, 8 goes in here. We get a 4, 6 pair. 8 is from the population of greenlinesses. So we must greenlify this cell. Still don't apparently know what these digits are. Ah, there's a sort of X-wing on 9s. Where does 9 go in this column? It's got to be in one of these two squares. Can we put 9 on a line? 3-cell line. Yes, I think we can. Is this circle restricted? This can't be 2, 3, 4 or 5. Okay. By Sudoku, that is. Okay, so we know it's not 1 or 9. So it's not 1, 2, 3, 4, 5. It could be 6, it could be 8, it can't be 9. So this is only 6 or 8. And if it's 8, oh, if it's 8, that's a 7, 9 pair. Good grief. Okay, so this is 6. Which means there's a 6 over here, look, by Sudoku. This, right, so that's not 6 and 8 now. So this is 5 and 9. So these have to add up to 12 without using 5 or 9. So they've got to be 4 and 8. Which means this square, after all this, has become a 1. And there's a 4, 7 pair here. So this has become an 8. This becomes a 4. This becomes an 8, this becomes a 2. We've got some Sudoku to do. What are these squares now? These are 1, 5 and 6. Come on. This is 8, so these are not 8. So this is a 2, 5 pair. This cell must be the next step, mustn't it? This sees lots and lots of digits. So this could be, maybe it could be a 2, I'm not sure. That would force this to be a 1, 3 pair. I don't know, that might be possible. Can this be a 3? Maybe. Can it be a 4? No. Can it be a 5? Maybe. Can it be a 6? No. Can it be a 7? No. Can it be 8? No. And it can't be 9. So this is only 2, 3 or 5, which means these two squares add up to either 4, 6 or 10. 4, 6 or 10. So this digit, if it's 4, this is a 3. If it's 6, this is a 1 or a 5. Oh, that's horrible. And if it's 10, oh goodness me, it can probably be anything. It can be, oh no, it can't be 9. Oh, this can't be 5, I don't think. Because I can't see a way of making those two digits add up to 10, although I've just thought of double 5. Oh no, sorry, I can't do double 5 if that is a 5. Although that would have the correct average, it would break Sudoku. So if this is 5, I can't do 1, 9, I can't do 4, 6. Okay, so that's just not 5. That's going to be important, I think. So if this is 2, this is a 1, 3 pair. If this is 3, this is a 1, 5 pair, but I don't know the order. So this is never 6, maybe. Maybe that's the point. Oh, that's useful if that's true. Yeah, I think that must be true because we're so low on the total now. These have a maximum value of 6. There's no way that can be 6. So this is a 6. So 6 is in one of those two positions in column 3. Oh no. I don't know. I'm not sure. There's a 4 in one of those squares. Again, I sort of think that I'm clutching at straws now rather than understanding what's going on. Can I get this digit? Maybe. Well, it's odd. Okay. Well, if it's odd, it's got to be 3 or 5 only. It's odd because it sees all the even numbers. And once we know it's odd, it can't be 1 or 9 because it's in a circle, and it turns out it can't be 7. So this is 3 or 5. Ah, that means this is a 1 by Sudoku. Now, it is outrageous that I'm made to do Sudoku so early in this puzzle, Miky. But look, that's a 3-5 pair. So this is a 1, this is a 5. That means this is a 1 or a 3. Well, it can't be a 1, because then this would have to be a 1 by averaging. So that's a 3, this is a 2. That's a 2, that's a 5, that's a 3, that's a 9. Therefore, this looks like it's got to be a 4-9 pair to me. And therefore, this has got to be a 7-8 pair, I think. Somehow not resolved. This is a 1 and a 3. No, it's not. It's a 1 and a 5. So those two squares are a 6-8 pair. I'm just staring at this in the hope it yields something. These are 1, 2 and 7. Let's do that in central pencil mark mode. That's not a 2. This column needs 1, 7 and 9. Can I use... Oh, this 3-5 pair. Right, that's not 3. Oh, the 1... Right, Sudoku, of course. 1, 2, 9. 9, 4. Here we go. This is no longer 9. So this column now, 6s, 7s and 8s have not been placed. So 6s, 7s and 8s at the bottom. I think we'll be able to use the maths on this circle. Let me just think about this. 9 here means this is 9, this is 3. So that's 2. Well, we definitely can do some maths now. This is a 3-5 pair. Ooh. Oh, I see. And look, it's a deadly pattern, but it's going to be sorted out by this circle. So, oh, well, okay, this can't be 3, because then this would need to be a 4, and it doesn't seem to be able to be. So that's got to be 5, which means we're looking for an average of 5. So these add up to 10, which makes this 8, which makes this 8, this 7, this 6, this 5, this 3, this 3. Oh, we might be about to get a visit from little people. Oh no, this is pressure now. 6, 3. I've underestimated timings today. There's about to be an explosion of noise. Oh no, come on, Simon. Right, what's going on with this circle? We've got 3 digits here that must add up to 18. 3 lots, 18. That feels quite challenging. So let's think about how we're going to do that. Well, yeah, okay, this is not a 1, because if that's a 1, that has to be an 8-9 pair. But then I can't put 9 in this column if this is a 1, because this will be an 8-9 pair, and that can't be a 9. So this is not a 1. So this is 7 or 9 now, which means if this is 7, this adds up to 11. The problem is that that doesn't look... Well, if that's 7... Oh, that will be 4, 5 then, won't it? Because I've forgotten about my white Kropki dot. Right, let's think about that. So if this is 7, this adds up to 11, but it doesn't use... Oh, that I don't get rid of any more options. That becoming 4, 5 eliminates 4, 7 and 5, 6, which are already eliminated. So this would be 2, 9 or 3, 8. What about if this is 9? If this is 9, these add up to 9. And they're not 3, 6. I don't know. This doesn't seem very easy, actually. What about... Ah, look, I can do Sudoku. Of course it's always going to be Sudoku, isn't it? So this hasn't got 4, 5 and 7 are left to place. This column needs 1, 4, 7, 8. So that can't be 5, look. No. If that's a 7, that 795 would go in, wouldn't it? If that's 795, 795. This becomes a 4. 7954. 7. Hang on. Our Maverick's taken off now as well. I'm getting bombarded from all sides. 7954. That's going to put 45 here. Oh, this is getting too complicated. I think there's something going on. I just can't understand how to think about it properly. I suspect that I've got some Sudoku to be doing. No, these columns are horrible, actually. They can't do anything in these columns. It's got to be these. I think it's got to be this row somehow, these two rows. Possibly with this white dot. Or this arrow. Seven, 9. What does that do? It makes this 5. It makes this 4. It puts 4, 5 here. Hang on. Where am I putting 5 in this box then? Has that disappeared as a possibility? Let me think about that again. If this is 7, this becomes 9, this becomes 5. So this can't be a 5, and it is a 4. But once this is 4, I've got to put 4, 5 on this dot. And then 5 can't appear anywhere in this box, so that doesn't work. Right, so this is 4. And this is 7. And now this is not 7, this is not 7. This is not a 4 combination. And now I've got a 5, 7, 9 triple in row thingy thing. So this is not a 7. So these squares are from 1, 2 and 8. But I still don't know where the 8 goes. Well, that's the kind of thing that's going to resolve this. Or can we do this some other way now? There's definitely a 2 over here. If that's 2, this will be a 7, 9 pair, won't it? 2 here, 7, 9 pair. This will be a 1. That will be a 7. This will be a 7. 2 and 7 and 9. That's going to have to be a 9. I don't even know if that's possible or not. I'm sort of losing track of all of the various options here. Wow. Oh, look, that can't be 8. I'd not noticed that. Maybe that's helpful. I'm really not sure it is, actually. One. Oh, that can't be 1, actually. Because if this is 1, I have to put 8, 9 onto this arrow. And that's going to have to be the 9, and that's going to break this square. So this is only 2 or 8 now. So we're very slowly whittling this down. So perhaps I've just got to try and work out what this digit is, and maybe it will, or everything will be either rendered possible or impossible. So let's think about that. Okay, so if this is 7, these have to add up to 11, which would have to be a 9 here add a 2 here, or a 3 here, and an 8 here. And if this is 9, these have to add up to 9, which would be 2, 9, 2, 7. Is that possible? Or 8, 1. That's 7. 7 doesn't work, so that becomes 1, 3, or 9. It's really close. It's really close to forcing interesting stuff. 5, 7, 9. 1, 2, 8. Or maybe there's a simpler way of thinking about this. Maybe I can I just assume? Yeah, okay, here's the way to think about this. Right, I don't know at what point this has been available, but it's now available. If this is a 7, 8 pair, where do you put 3, 4 and 5 in this box? If that's a 7, 8 pair, it seems to me that 3, 4 and 5 can only go in those 2 squares just from the pencil marking, and that cannot work. So this must be a 4, 5 pair, and if that's a 4, 5 pair, that's a 7. There we go. So 7, 5. Please let that do it. Please. That's 8, because we know there's a virtual white dot, don't we? So this is 1, this is 4, this is going to do it. Here we go. 5 and 9 go in. That's now a 9, so this is now a 7, which makes this a 1. And we know these have to add up to 11, but we can't do 2, 9 anymore, so we have to do 8, 3. And if we're doing 8, 3, I'm guessing everything is going to work now. 9, 7, 7, 2, 8 here, 8, 6, 6, 4, 4, 5, 5, 1. This square here is a 2, and that's a 1. What a brilliant puzzle. Oh, 4 and 7 over there as well. What a brilliant puzzle. Oh, 0. It took me 0 again. I've done enough. I've done enough divisions with remainder 0 in the last hour and 12 minutes. That is a fantastic puzzle. My goodness, not easy. I can understand, I think, why this has only got something like 4 or 5 solves on Logic Masters Germany. It's breathtakingly clever. I would love to know if I was meant to think about this. I think it's all about the perimeter, actually. Now, upon reflection, it seems to be you have to understand how the modularity flows around the perimeter. It's quite beautiful. The way that this digit turned out to be a 1 is that's one of the, for me, and my experience of how I got to that digit was one of the most spectacular naked singles we've ever seen on the channel. Absolutely breathtaking. Mikey, take a bow. Let me know in the comments how you got on. I'd love to know. I'm going to peruse the comments with interest, and I'm hopefully going to find that most of them are kind. And we'll be back later with another edition of Cracking the Cryptic.